welcome everybody to physical, chemical, water monitoring. So what we've got on our agenda for this evening is we're going to learn about common water quality variables, what they mean, how and why they're monitored. We're going to learn some global water watch techniques for physical and chemical monitoring. And we're going to learn about some other types of things that we can monitor that are a little in addition to the standard global water watch test. So first of all, let's just talk about what are some common water quality variables that are monitored. So this is an excerpt from King County website. So King County does some streams monitoring, and they've been doing it for a long time. And they use a metric called the water quality index, which is kind of a summary metric of a variety of different variables. And these are the variables that they monitor. So these are common ones that are monitored with regard to physical and chemical variables in water quality. So just going through the list, temperature is an important variable. We'll talk about each of these variables in turn, but that's an important one because it relates to dissolved oxygen, and things that live in the water kind of expect the temperature to be a certain level. So around here in particular, if water temperature is too warm, that's a problem. Similarly, dissolved oxygen, things that live in the water need the oxygen. So if it's too low, that's a problem. pH usually isn't a problem, but that's that's the acid-base scale, and it needs to be within a certain range. Bacteria will be the subject of another class, but that is something that's monitored with regard to recreational contact and human health. Nitrogen and phosphorus are nutrients that are involved with, they can relate to what's called eutrophication, where you have excess plant growth, and they can also be related to algae blooms. So those are some important variables. Total suspended solids is kind of an indicator of how much stormwater is getting into a stream. It's kind of an indicator of that. And then it's also has a close relationship with conductivity. And then turbidity is a measure of water clarity. So those are some of the most common ones that are monitored. And we monitor, you'll see the Global Water Watch monitors some, but not all of these. So there's Washington Administrative Code regulates certain types of uses, and it also regulates certain particular standards for these variables. So in terms of uses, the uses that are regulated are salmon spawning, rearing, and migration, primary contact recreation, which means people using the water, getting in the water, using the water supply for people and animals to drink, wildlife habitat, harvesting, which is things like shellfish harvesting and boating, and also just aesthetic values. So these are all uses of water. And then in terms of the variables that are regulated, so temperature is regulated, dissolved oxygen is regulated, dissolved oxygen saturation, we'll talk about what that means, but essentially it's how much oxygen is in the water relative to what's the potential that could be there at a given temperature. It's regulated. pH, bacteria, turbidity are all regulated. Nutrients are not formally regulated under the freshwater standards. Total suspended solids and conductivity is not regulated. That PPD 6-Q is a new contaminant of concern, or I should say it's recently learned to be a contaminant of concern with regard to pre-spawn mortality in salmon. They're just developing approaches right now to that, so that's not regulated. And then there's lots of different specific chemicals that could be pollutants that are not regulated. So some of the key ones are regulated, but there's a lot of things that are not as well. Another thing to consider with regard to physical and chemical water quality monitoring is there's different ways that data can be collected. So this is an example of an electronic meter. So this type of meter has a probe and you'd use this to, you can measure some of the same variables that we're measuring right now. You would calibrate this meter with some different calibration solutions. Then you would put it into your water body, and you can read things like temperature, dissolved oxygen, nitrates, total suspended solids, conductivity. This is typically used, it's used in some nonprofit programs. These meters cost several $1,000s a piece. So generally for a widely distributed volunteer program, they're not necessarily the best use, but there are some volunteer programs that do use these. But these would be something that would be typically used by like an agency, government agency. Or another approach is to collect samples, take them back to a lab, and then have the lab do the analysis. So that, again, that's often done, like, for example, in some cases, like if a government entity is testing for a particular thing that they can't test with a meter, they'll send it back to a lab. Or if they, for instance, some use this approach for bacteria. There's also things called fixed data loggers that they're fixed in place. If you always want to monitor the same place and have continuous data readings, and there are some of these around on some of our different water bodies. So you might want to measure, for instance, flow. So like the US Geological Survey has got flow meters on different rivers. So that's an example of another type of way that water data is collected. And then finally, volunteer programs like ours often use sort of a little chemistry kit for collecting water data. And that's what we'll be talking about this evening, is the kit that our program uses. So this is the equipment that we use. This is what it looks like. So this is a Lamont kit, and it is actually based on what is used by Alabama Water Watch, because Global Water Watch and Alabama Water Watch started at about the same time in Auburn University. And so essentially they share pretty much the same techniques. And in fact, we'll watch some training videos this evening that are from Alabama Water Watch. But that's what it looks like. It's just essentially a little chemistry test kit. And then we have some other peripheral supplies, pens, pencils, some clear water that we can use for our turbidity sample, a waste container. So and then a box to carry it all in. So this is the equipment that we carry. The different variables that are monitored or measured by the Global Water Watch test kit are temperature, pH, dissolved oxygen, alkalinity, hardness, and turbidity. And alkalinity and hardness are interesting because those are not ones that are necessarily monitored like as part of the water quality index. They are part of the Global Water Watch suite of things that they monitor, and they are actually useful as kind of give you a baseline of what's going on with kind of the calcium, magnesium, the different ions that are present in the water. So we're going to talk about some general principles, and then we'll get into some specifics. So in terms of general principles, one is just try to work off the directions. So most of our test kits will have an abbreviated set of directions with them. If you don't have that, you can use the manual, but essentially you want to make sure you're following the directions, because especially some of the tests like dissolved oxygen can be really detailed, and it's just hard to make sure you're doing all the steps properly if you're just trying to do it by memory. Another thing is don't forget to record the results as you go along, because you'll find if you get about 3 tests in and you think, oh yeah, what was my temperature, or what was my dissolved oxygen, I forgot to write it down. So just keep recording things. This is an example of what the data sheet looks like for Global Water Watch. Another thing is the reagents all have an expiration date, and typically what we do, as it goes in and out of the kit, you can see where it's printed on there, it'll tend to get rubbed off. So we tend to write it up on the shoulder of the bottle, but you want to make sure before you do your monitoring that everything is complete and present and that they're not expired. We also, as a best practice, we don't just discard our waste chemicals on site. What I've been told is that they are okay to go into the sanitary sewer. So we collect them, and then when we're done with our water monitoring, we just put them into the sanitary sewer drain. So just down a sink or a toilet is okay. But just as a best practice, we don't discard them on the stream site. Key principle is having no information is better than having wrong information. And what this means is if you think you might have forgotten a step or you didn't quite do that test right, just do the test over. So just make sure that you've done it correctly before you record your result. Another tip is you can just kind of stay organized. You can use that kit, work out of that kit to stay organized as you're monitoring. If you find that you start putting tubes down here and there, and you may drop them, break them, lose them, spill them, etc. So that's just a helpful tip to keep organized. So another tip is there's a concept called a meniscus, and the meniscus is essentially that little curve that's caused by surface tension in the water. And so as you fill your different reagent containers with sample water, you want to make sure that the bottom of that meniscus is even with the line. Another tip has to do with dispensing drops. So a lot of these tests involve dispensing drops of reagents. So what you want to do, and of course we'll go over all this in person, but while the bottle's right side up, you squeeze it, then you tip it upside down. That means invert it. Then you release it, so you draw a little bit of air back in. Then you start dispensing your drops, because if you don't do that, you'll find that the drops may run out as opposed to dispense a drop at a time. There's a concept in all these tests, which a lot of these are titration-based tests. What that means is you put some reagents into the sample and it causes it to change color. And then ultimately you're going to add some other reagents until the color changes. So the first thing is, before you start adding the other reagents to try to titrate it, you need to make sure that everything is dissolved, mixed fully. So some of these involve tablets. You want to make sure that they're dissolved fully. Then you're going to add one drop at a time and swirl it to mix. And you want to essentially, you want to give enough time for that reaction to happen. So you don't want to just drop them in there really fast. And then you're going to keep adding drops of the reagent until the color no longer changes. At which point you add one more drop just to confirm it's not changing, but you don't count the last drop. So if, like, let's say on that third picture, it's still a little bit purple, now it's blue, we'd add one more drop, but assuming it didn't change anymore, it didn't get any bluer, we wouldn't count that last drop. All right, let's get into some of the specific tests. So temperature is a very important variable. It affects the properties of the water. Cold water holds more dissolved oxygen. You'll discover that the tests that we're doing, like the reagents take more time to dissolve in cold water. And in particular, why it's important around here is that salmonids need cold water, and that can be a problem. With some of our rivers locally, and with climate change and warming, and with riparian zones being cut down and cleared, the result is that some of our water bodies, like for instance the Sammamish River, can get too warm and actually cause a barrier to salmon migration. So this is a chart from the Washington Administrative Code, and it shows what the regulated standards are for water temperatures. And so you can see salmonids need pretty cold water. Okay, so let's just talk about some monitoring tips. So we're just using these thermometers that are only accurate to about 1/2 degree. To avoid affecting the temperature, you don't want to hold it by the bulb, by the bottom, because you could, the warmth of your fingers could affect the result you get. And then if you just have one thermometer, you want to measure the air temperature before you do the water temperature, if you're just using one thermometer for both, because if you do the water temperature first, you're going to get some evaporative cooling. And then you'll record it on your data sheet in Celsius to the nearest 0.5. And I'm going to show a little quick video on air and water. Can everybody see that? It says air temperature. Okay.
Air temperature. Always take air temperature before water temperature for the most accurate readings. Upon arrival at your site, find a place in the shade where you can place, preferably hang, the dry thermometer. If you do not have shade, you can create shade with your body. Allow the thermometer to remain in the shade until the temperature stabilizes. This will usually take 2 to 3 minutes. To read the temperature, hold the thermometer by the eyelet at eye level. Remember, never touch the bulb of the thermometer, as you will end up measuring your body temperature instead of the air. Read and record the temperature to the nearest ½ degree Celsius on your data form. Once you finish measuring air temperature, you are ready to measure the water temperature. If possible, find a location that is shady and in the same area of the water body where you plan to collect your sample. Submerge the thermometer in the water about 2 to 3 inches. It may be necessary to anchor the thermometer to prevent loss in strong current, body water, or deep water. This can be done by tying a cord through the eyelet and attaching it to a stable object. If no such object is present, you can hold the thermometer in place. Try to avoid allowing the thermometer to rest on dark rocks, as it will affect the temperature reading. Leave the thermometer in the water for 2 to 3 minutes. Once the temperature stabilizes, read the thermometer while it is still submerged or immediately after removing it from the water. Record the temperature to the nearest ½ degree Celsius on your data form.
Is everybody able to see that okay? Okay, so that's a pretty straightforward test. Let's talk about pH, our next test. And so pH is just the acid-base scale, goes from 0 to 14. And the optimum for fish is essentially fairly neutral. So they can tolerate a little bit of range from acid to basic, but it needs to be essentially pretty neutral. And so this says 6 to 8.5. The regulation is 6.5 to 8.5 is the pH range. So in terms of the procedure, so you're going to use this particular tube in the kit. You're going to rinse it 3 times with sample water, fill it up to 10 ml line, which is, you'll see it at the top. You can add 10 drops of this wide range indicator, cap it, invert it, and then you'll get a uniform color. And then you're just going to compare it to the color indicator by matching the color. So it's a pretty straightforward test. And I think what I'm going to do is, that is such a simple test, I'm going to skip that video. Hardness is a concentration of calcium and magnesium in water, and it's mostly based on groundwater. A certain amount is required by different living organisms, like, for instance, well, people need it to make bones, fish need it, shellfish need it to make shells. And what you may discover is what you'll typically find when you start monitoring is you're going to get kind of a baseline level of what's normal. And you may get a little bit of fluctuation up and down. And so what you'll find is that, one, you may see a lower level than normal when there's more water in the stream, like more storm water. But if you find a really extraordinary number, then that's when you need to do some detective work and figure out what's going on. Okay, so we're going to watch a little video on how to do hardness.
Total hardness. This video will show the proper method for collecting water samples and conducting a test to determine the total hardness of a water sample. When monitoring in coastal waters, conduct a salinity test first. If salinity is detected, do not perform the hardness test. For this test, you will need the hardness tube, code 4488, hardness reagent number 5, code 4483-E, hardness reagent 6 tablets in a blister pack, code 4484A-J, and hardness reagent 7, code 4487WT/H. Remove the hardness tube from your kit. Rinse the tube 3 times with water from the site you are sampling. Fill the tube with sample water. Hold the tube at eye level and flick out excess water until the bottom of the meniscus touches the 10 ppm line. This is your 10 parts per million, or ppm, sample. Locate hardness reagent number 5 bottle. This bottle has a built-in dropper, so uncap the reagent bottle. Gently squeeze it in the upright position to let some air out, and then turn the bottle upside down while releasing the pressure. When dispensing the reagent, take care to hold the bottle vertically. This ensures uniform size drops. Add 5 drops to your sample and gently swirl to mix. Locate the hardness reagent number 6 tablet blister pack. This reagent is in tablet form and is very soluble. Take care not to touch the tablet or allow any water to come into contact with the tablet prior to dispensing it into the hardness tube. Hold the blister pack with the foil facing down over the opening of the tube. Press on the opposite side of the blister pack to dispense a single tablet into the water sample in the tube. Carefully cap the tube with the large blue cap. You will only need to partially cap the tube. Pressing the cap down completely on the tube could cause the glass tube to break. Gently swirl the tube until the tablet dissolves. Typically, a pink color develops as the tablet dissolves. Next, we will titrate our sample using hardness reagent number 7. The hardness reagent number 7 bottle also has a built-in dropper, so uncap the reagent bottle, gently squeeze it in the upright position to let some air out, and then turn the bottle upside down while releasing the pressure to create the vacuum to give you more control over the drops. When dispensing the reagent, take care to hold the bottle vertically. We will count how many drops of hardness reagent number 7 it takes to cause the sample to change to a blue color and to stop changing color. In other words, we will reach the titration endpoint. Add 1 drop of hardness reagent number 7 at a time to the water sample in the tube. Gently swirl to mix between each drop. Be sure to allow time between drops for the color change to occur, especially during cold weather. You will need to know how many drops you add to your sample, so don't forget to count. You can keep the bottle in the vertical position throughout the test. Continue adding single drops of the reagent until the pink color changes to blue and the additions do not cause a color change. Once you think you've reached the titration endpoint, or the point where the color is no longer changing, add 1 more drop. Do not count the last drop if there is no color change after its addition. In some cases, the sample water will turn blue after the hardness number 6 tablet dissolves prior to titration. This could indicate that there is no measurable hardness. However, you will need to titrate to confirm that no color change will occur with the addition of hardness reagent number 7. If you add a single drop of hardness number 7 and no color change occurs, record 0 mg/L for total hardness on your data form. On the data form, record the number of drops it took to reach the titration endpoint. Also on the form, to calculate a total hardness value in milligrams per liter, multiply by 10 the number of drops of hardness reagent number 7 used. Note that if total hardness routinely exceeds 200 milligrams per liter, conduct the test by filling the hardness tube to the lower line, 20 ppm, and multiply by 20 the number of drops of hardness reagent number 7 used.
pH. This video will show the proper
Okay, did anybody have any questions on the hardness test before I move on? Okay. All right, so the next test that we're going to see is the alkalinity test. And so alkalinity sometimes gets confused with the term alkaline, but alkalinity is a measure of buffering capacity of water. So it's essentially how resistant is the water to changing pH. So if it has higher alkalinity, it's more resistant to pH changes. Again, there's not a regulated standard on this, but generally speaking, things that live in the water want to have it kind of in that middle range. So watch a short video on how to do the alkalinity test.
This video will show the proper method for collecting water samples and conducting a test to determine the total alkalinity of a water sample. For this test, you will need the alkalinity test tube, code 0970S or 0289, BCG MR tablets in the blister pack, code 2311J, the plastic dropper, code 0352, and the alkalinity titration reagent B, code 4493PSH. Remove the alkalinity test tube from your kit. Rinse the tube 3 times with the water from the site you are sampling. Fill the tube with sample water. Hold the tube at eye level and flick out the excess sample water until the bottom of the meniscus touches the 10 milliliter line. This is your 10 milliliter sample. Locate the BCG MR tablet blister packs. Tablets are very soluble. Take extra care to not touch the tablet or allow any water to touch the tablet prior to dispensing it in the alkalinity tube. Hold the blister pack with the foil facing down over the opening of the tube. Press on the opposite side of the blister pack to dispense a single tablet into the water sample in the tube. Carefully cap the test tube with a large blue cap. You only need to partially cap the tube. Pressing the cap down completely on the tube could cause the glass tube to break. Gently swirl the tube until the tablet dissolves. A blue-green color will likely develop as the tablet dissolves. If a pink or pink-gray color develops after you have added the BCG MR tablets and before titration, it could indicate that there is no measurable alkalinity. You will need to titrate to confirm that no color change will occur. If you add a single drop of alkalinity titration reagent B to the sample and no change occurs, record 0 milligrams per liter for total alkalinity on your data form. Next, we will titrate the sample by adding alkalinity titration reagent B with the dropper with either an orange or black bulb. We will count how many drops of alkalinity titration reagent B it takes to change the color of the sample from blue to pink, and more specifically, for when the color stops changing or reaches the titration endpoint. To begin, fill the dropper with the reagent by squeezing the bulb, inserting the dropper into the reagent bottle, and releasing the bulb. Review the dropper to make sure there are no air bubbles. If air bubbles appear in the dropper, squeeze the bulb to empty the dropper and refill it. When dispensing the reagent, take care to hold the dropper vertically. This ensures uniform size drops. Add 1 drop of reagent at a time to the water sample in the tube. Gently swirl to mix between each drop. Be sure to allow time between drops for color change to occur, especially during cold weather. You will need to know how many drops you add to your sample, so don't forget to count. Continue adding single drops of the reagent until the blue-green color changes to pink and eventually no longer changes with any addition. Once you think you have reached this titration endpoint, or the point where the color is no longer changing, add 1 more drop. Do not count the last drop if there is no color change after its addition. Record the number of drops it took to reach the titration endpoint on your data form. Also, to calculate a total alkalinity value in milligrams per liter, multiply the number of drops of alkalinity titration reagent B used by 5 and record this value on the data form.
Okay, so that was the alkalinity test, which is similar to the hardness test, but a little bit different. Next, we're going to talk about turbidity. And I'll say that from a standpoint of the test that we do, turbidity is one of the more important tests, and it's one of the more important things for you to keep your eyes out as a water monitor. It's a measure of the relative clarity of water, and things that affect that can be natural or from human cause. This is an example of Little Swamp Creek in Kenmore after some runoff from a construction site caused the creek to become turbid. And so that's the kind of thing that you want to keep your eyes peeled for as you're out water monitoring, or as you're just out walking around looking at creeks. In streams, if you have chronically high turbidity, it can cause sedimentation, so it could bury gravel beds, the salmon reds where they lay their eggs, or other creatures that live in the gravel. And the dirt also provides kind of a transport mechanism for other pollutants such as metals and bacteria. So the way that we measure turbidity is there's a few different ways we measure turbidity. We've got the Global Water Watch tubes, and they measure in something called JTUs. NTUs is, we also have larger turbidity tubes that we have kind of augmented our Global Water Watch kits with, because NTUs is the unit of turbidity that a regulatory agency would understand. If you came and said, hey, I found 50 JTUs, they wouldn't necessarily understand it. So it's still, it's a useful test to just compare month to month. But if you did need to communicate with somebody about a spill or a high turbidity level, you want to use NTUs. There's also meters as well as turbidity tubes, which digital meters that can measure it at a higher degree of accuracy. So with the JTUs, the highest degree of accuracy that you could say is you've got less than 2 JTU, and with the NTU tubes, typically the highest degree of accuracy that we can say is less than 8 or 10 NTUs. So the global water watch method uses these two tubes. So one is labeled control and labeled sample. So the control is going to get essentially bottled water or tap water in it. And the sample is going to get water from the creek. And you're going to compare by looking down through the tubes. You can look at the clarity of the different samples. And then you'll add some turbidity reagent and then compare it again. And you keep adding it until the control is more turbid than the sample, at which point you won't count that last addition. So we're going to watch a short video on how to do turbidity measurement.
Turbidity. This video will show the proper method for collecting water samples and conducting a test to determine the turbidity of a water body. For this test, you will need two turbidity columns, code 0835, standard turbidity reagent, code 7520-H, and a stirring rod. Locate the turbidity columns in your kit. If you're using your own kit, we recommend labeling one of the turbidity columns with an S for sample and the other with a C for control or a T for tap water. Rinse the S column 3 times with sample water from the water body. Then fill the column completely. Flick out excess water until the bottom of the meniscus is at the 50 milliliter line with sample water. Place the S column on a level surface, like in the center of your kit. Position yourself so that you can look down into the column through the opening, preferably from a distance of only about 6 inches. You should see a black dot on the bottom of the column. If the black dot on the bottom of the column is not visible when looking down through the column, find the clear stirring rod and stir the water sample in the column. Flick out excess water until the bottom of the meniscus is at the 25 milliliter line with your water sample. Look down into the column to find if, with that sample volume, you can see the black dot on the bottom of the column. When successfully seeing the black dot on the S column, rinse 3 times your second column, the one labeled C for control or T for tap water. Fill the second turbidity column with the same amount of bottled, distilled, or tap water. Place the columns side by side with the column bases almost touching. Make sure that they are on a level surface, like in the center of your kit. Position yourself so that you can look down into the columns through the openings, preferably from a distance of about 6 inches. This time, you should see a black dot on the bottom of both columns. For this test, you will be comparing the clarity or the fuzziness of the black dots in the bottom of the 2 columns. Do not consider the color of the water. Typically, the tap water in the T column will be clearer than the sample water. Therefore, the dot at the bottom of the T column will appear clearer, sharper, with less fuzziness. We will determine the turbidity of our sample water in the Jackson turbidity units by counting how many additions of standard turbidity it takes to make the tap water have the same level of turbidity as the sample water. To start, find the standard turbidity reagent and the dropper that is marked at the 0.5 milliliter line. Shake the reagent vigorously and then fill the dropper with 0.5 ml of the reagent. To do so, hold the dropper vertically, squeeze the bulb, and then insert the dropper into the reagent bottle and release the bulb. The dropper should fill with no air bubbles. If air bubbles get into the dropper, squeeze the bulb to empty the dropper and refill it. Hold the dropper at eye level and carefully squeeze the bulb and expel excess reagent to the desired sample volume marked 0.5 ml. Find the clear stirring rod and stir both columns. Tap off excess water between columns to prevent contamination. We recommend that you hold onto the foot of each column when stirring to prevent spills. Look down at the black dots at the bottom of the columns. If the T column is clearer than the S column, you will need to add the entire 0.5 milliliter of the reagent in the dropper to the T column. Make sure you dispense all the reagent in the dropper. Using the stirring rod, stir both columns, then look at the dots again. If the dot at the bottom of the T column is less fuzzy than the dot at the bottom of the S column, shake the standard turbidity reagent and collect another 0.5 milliliters in the dropper. Add the entire 0.5 milliliter to the T column, stir both columns, and observe the black dots. Continue this process of adding 0.5 milliliters of the reagent to the T column until the dots in both columns appear to have the same fuzziness or clarity. You will need to know how many additions you add to the control column, so don't forget to count. Once you feel the dots at the bottom of the T and S column have the same clarity, or in other words that you have reached the titration endpoint, add one more 0.5 milliliter addition. If the last addition causes the dot at the bottom of the T column to be fuzzier than the S column, it confirms that the previous addition was the endpoint. Record the number of the 0.5 milliliter additions you added to the control, not counting the last addition. You will notice on your data sheet that to calculate turbidity in JTUs, you need to multiply the number of additions by 5 if using a 50 milliliter sample. On your data form, you will notice that you also have the option of multiplying by 10 if using a 25 milliliter sample. In some rare cases, it is possible that the dot at the bottom of the S column is still not visible after reducing the volume to 25 milliliters. If this happens, record the turbidity as THTM, or too high to measure, in the comment section of your data form. In some cases, your 50 milliliter water sample might be so clear that the dots at the bottom of T and S columns are equal before adding the standard turbidity reagent. In this case, you should still add one addition of 0.5 milliliters to confirm that this is the case. If the T column is fuzzier than the sample after one addition, you should not count the addition. On your data form, report the number of measured additions as 0 and report JTUs equal 2. This is because it is very unlikely for a natural water body to have 0 turbidity. Also, the detection level for turbidity that is possible with this test is limited. Thus, reporting 2 JTUs for a 0 reading compensates for this fact.
Okay, so that was turbidity with the Alabama Water Watch, Global Water Watch kit. So we're going to talk a little bit about another way to measure it, and that's with using the NTU turbidity tube. So the way that you use this tube is, again, you're going to gather a sample of water. If the water body is deep enough, you can use the tube itself to collect the water, but the tube is about 30 centimeters long. So in some cases, if you're just working on a small water body, that won't work. So you may need to have a separate container that you fill the tube with. And what you're going to do is fill it to the top and look down, and at the bottom of the tube, there's a thing called a Secchi disc, which is this little marker. And kind of like the black dot in the previous test, you're looking to see if you can see that Secchi disc. And if the tube is all the way full and you can see the Secchi disc, then you're just going to record the minimum level that's detectable with this test, which is, I believe, 8 NTUs. If you can't see it, then what you're going to do is you're going to release water with a little drain until the water comes out, until you can just barely see the Secchi disc, and then you'll record the level. And then you take a look at a chart, and this chart just expresses a mathematical relationship between depth of water and turbidity in NTUs. And so the left-hand side of the chart gives you a centimeters from the bottom of the tube, which the tube is marked in, and then the chart gives you the corresponding number of NTUs that you would record. So if the distance was, this is actually for a 60 centimeter tube. If it's over 60, it would be less than 8. And I'm sorry, I misspoke. These are 60 centimeter tubes. And then you would record that on your data sheet under the other observations box. We also do have a handful of these, what are called direct read tubes, in which case the NTUs are printed right on the side of the tube. So again, you just fill the sample tube, look down through the tube to see if you can see the Secchi disc. And if you cannot, then you release the water until you can just see that Secchi disc, and then you read the number directly on the tube. Okay, moving on to the next test, dissolved oxygen. So again, we talked about how oxygen is important for different things that live in the water. Plants may produce the oxygen, aquatic animals need the oxygen, and it gets into the water a couple different ways. One is just by physical action of water, such as like flowing over a waterfall or turbulent flow can kind of get oxygen into the water. Also, plants can produce oxygen, and that's one of the primary sources of oxygen in lakes and in the ocean. But conversely, things like plants decaying and other organic material decaying can remove oxygen. So kind of have both effects going on there. So this is a chart from Global Water Watch Manual that just shows different levels of dissolved oxygen and what is typically what's not good enough or what is typically good. Warm water fish generally can tolerate lower dissolved oxygen, whereas salmonids need a higher dissolved oxygen. And this is the chart from the Washington Administrative Code that shows what the different minimum levels are for different types of water uses. So you can see that typically the minimum for essentially habitat as opposed to just passing through is about 10 milligrams per liter, which is a fairly high dissolved oxygen. Dissolved oxygen and temperature have an inverse relationship, and so that's one of the reasons why salmonids need cold water, is because when the water's colder, it holds more oxygen. This is an example of a chart out of our Global Water Watch database that just illustrates that. So we're going to talk about performing the test. So this is probably the most complicated test that we do. And you essentially do the test in parallel yourself. You conduct it twice simultaneously to make sure that you're doing it correctly. Essentially, you're building a double check into the process. So the first step is collecting the sample. Then you add some reagents to fix the sample. And then you go through a titration process to come up with your actual dissolved oxygen number. And essentially, the way this test works is this little syringe-looking object is called the direct reading titrator. And this somewhat complicated test is designed such that at the end, let's say it reads from 0 to 10. Let's say that you put in 9.4 units of this final reagent. That means that your dissolved oxygen is 9.4 milligrams per deciliter. So that's kind of the quick overview and the why and the how of this test. So we're going to go through some videos that are going to go through this test in detail, but this is kind of what it looks like in a summary.
Dissolved oxygen. This video will show the proper method for collecting water samples to conduct a test to determine the average dissolved oxygen of a water sample. Step A, collecting the sample. To begin this portion of the test, you will need to locate the two water sampling bottles, code 0688/DO, in your test kit.
Make sure there are cones in the cap of each bottle.
You will use the water sample bottles in your kit to collect two replicate water samples at the same time and place in the water body. Collecting two replicate samples, also referred to as reps, ensures precision. To begin, rinse both bottles 3 times with sample water. To fill the bottles, it is necessary to hold both sample bottles in the same hand. This ensures that you are collecting replicate samples at the same place in time. Completely submerge the capped bottles under the water so that they are in an upright position that will allow the bottles to fill with water while all air bubbles escape. Avoid disturbing the substrate or stream bottom at the sampling site. Allow the bottles to fill completely underwater. Once bubbles have stopped emerging from the bottles, move or shake the submerged bottles to allow any additional air bubbles to escape. Do the same with the caps to make sure that there are no air bubbles in the caps. Replace the caps on the bottles while they were still submerged. Remove the capped bottles from the water and invert them to make sure that no air bubbles are trapped inside. If air bubbles are present, even if they're only in one bottle, empty both sample bottles and refill them with water again. Once a satisfactory sample has been collected, proceed immediately with the next steps. Step B, fixing the sample. This video will show the proper method for fixing the water samples so that you can complete the test and determine the average dissolved oxygen of the water sample. For this step, you will need manganese sulfate, code 4167-G, alkaline potassium iodide azide, code 7166/G, 1:1 sulfuric acid, code 6141-WT/G. Note that each of these reagents are considered hazardous substances. Take precautions not to splash the chemicals into your eyes. If you get reagent on your skin, rinse with water. Youth using these chemicals should be carefully supervised. Make yourself aware of and adhere to the recommended 4-H AWW safety protocols. Safety glasses, and in some cases gloves, may be required by some schools for student monitors. Before you get started, make sure you position the sample bottles on a level surface. This may be difficult streamside, so we recommend that you keep them in your kit, using your kit as a lab table. This will prevent spills and protect your hands from chemicals. We will begin by adding manganese sulfate to both of the sample bottles. The reagent bottle has a built-in dropper,
So remember to create a vacuum and hold the bottle vertically.
Uncap both sample bottles and add 8 drops of manganese sulfate to each sample bottle. Then, in the same way, add 8 drops of alkaline potassium iodide azide to each sample bottle. It is likely that the bottle will overflow as you add the reagents. This is okay and will not damage the kit. Cap bottles securely and rinse them in the water to remove traces of reagents that may be on the surface of the bottles. Mix the bottles by inverting them at least 10 times. At this point, a tan, cloudy precipitate will form. Allow the cloudy precipitate to settle below the shoulder of the bottles. Now, uncap the bottles again and add 8 drops of sulfuric acid, 1:1 to each sample bottle. Cap bottles and rinse. Repeatedly invert the sample bottles to mix until most of the dark brown flecks have dissolved. Be patient during this step. Brown flecks in DO bottles may take several minutes to dissolve, especially in cold water. Turbid water samples may contain fine particulate organic matter that may not completely dissolve. The flecks tend to be a more uniform size, shape, and color than the particulate organic matter. At this point, your samples are now fixed. This means the oxygen in the sample is chemically trapped and that contact between the water sample and the atmosphere will not affect the test result. Monitors have the option of holding or transporting fixed samples for up to 2 hours before further analysis. This is rarely necessary, but may be useful in some cases, including the occurrence of a storm that might prevent a monitor from completing the test stream side. Step C, titrating the sample. This video will show the proper method for titrating water samples as part of the dissolved oxygen test. For this step, you will need titration tube code 0608 or 0299, starch indicator code 4170WT/G, direct reading titrator code 0377, and sodium thiosulfate code 4169-H. This entire process should be completed for one sample bottle before starting the second sample. Rinse the titration tube 3 times with a small amount of the fixed sample from the first sample bottle. Be careful not to use too much of your sample so that you are sure you have enough to conduct the test. Pour the waste into a waste container or broadcast it over a vegetated area. Fill the titration tube to the 20 milliliter line with fixed sample water from the sample bottle. If you overfill, you can carefully flick the excess sample water into the waste bucket or onto vegetation so that the bottom of the meniscus is touching the 20 milliliter line. Remember, the sample contains caustic reagents, so use caution. Now add 8 drops of starch indicator to the tube and cap with the titration tube cap, which has a hole in the center. Gently swirl to mix. The sample should turn dark blue to black. You will need to fill the direct reading titrator with sodium thiosulfate by depressing the titrator and placing it into the hole in the top of the sodium thiosulfate reagent bottle. Invert both the bottle and titrator and draw out the titrant until the large ring on the plunger is opposite the 0 line on the scale. Make sure that there are no air bubbles in the titrator. If there are bubbles, you can push the sodium thiosulfate back into the bottle and refill. Keep the bottle inverted throughout this process. Sometimes you may need to do this several times to eliminate the bubbles. Next, insert the filled titrator into the center hole of the titration tube cap. Add 1 drop at a time of the sodium thiosulfate into the titration tube. Gently swirl the tube between drops. You do not need to count the drops for this test. Continue titrating by adding more drops, 1 at a time, until the dark blue or black solution turns completely clear. Hold the tube against a white background to be sure that the solution is clear and not faint blue. Note that it may take more time for the color change to occur during cold weather. Once the solution is clear, read the number on the titrator where the widest part of the plunger meets the line on the scale. Each minor division on the titrator scale equals 0.2 ppm or parts per million. Record the value to the nearest 0.2 ppm on your data form for rep number 1. If the plunger tip reaches the bottom line on the titrator scale, or 10 ppm, before you have reached the titration endpoint, refill the titrator to the 0 line with additional sodium thiosulfate and continue the titration. To determine the oxygen concentration, add the original 10 ppm to the second ppm value and record the total value. Repeat the procedures of this step for the second sample bottle and record the results for rep 2 on the data form. If the DO results for rep 1 and rep 2 are not within 0.6 ppm of each other, repeat the steps for titrating the fixed sample in the first bottle. If results still vary by more than 0.6 ppm, repeat the steps for titrating with the sample in the second bottle. If there are still not two results within 0.6 ppm of one another, you will need to repeat the entire test by beginning with sample collection. Leftover titrant or sodium thiosulfate in the titrator could have been contaminated with the water sample and should be discarded. Do not return leftover titrant to the bottle. As you can see, the dissolved oxygen test has many steps, and at times you have to wait for reactions to take place between the steps. For this reason, many volunteers like to begin with the dissolved oxygen test so that they can move on to the other tests while waiting for DO reactions to complete.
Okay, that was a little bit complicated of what test if you've never seen it before. So rest assured, you'll have plenty of time to practice in person and it will all become clear. But are there any questions right now? I'm going to go through a couple more tests. Okay, so that was the dissolved oxygen test, and we went through all the different components of that test. So we went through collecting the sample, fixing the sample, titrating the sample. Then when you're done, you also do a calculation called dissolved oxygen saturation. So this is essentially you're going to come up with a number, and you're going to compare the number that you have to the number that is possible that would be 100% saturation at that temperature. So for instance, let's say that our temperature was 20 degrees Celsius. So the maximum theoretical 100% concentration would be 9.07. So if we end up getting, instead of 9, let's say that we got 8.4 in our 2 reps, and we're going to average our reps. So if we got 8.4 and 8.6, we'd use 8.5 as our average. So we're going to divide that by 9 and then multiply by 100. That will give us our percentage oxygen saturation. So you can get an oversaturated situation. You don't want that either. That's not necessarily good. You might find that like the bottom of a waterfall, for instance. But if you had some artificial situation that created it, it could be bad. More typically, what you're going to find is you're lower than the theoretical maximum. So that's one additional thing that we do once you've collected that information.
Eric?
Yeah.
So some of the charts and things were switching back and forth between parts per million and milligrams per deciliter.
Good question. Those are actually synonymous.
Okay.
Yeah, it's funny. That's an excellent question, and it is kind of confusing, but yeah, those actually mean the same thing. Good question. So here's kind of your interpretation of the DO saturation. So again, this isn't something typically where we find that we're out of range, but it's something we want to check. Okay, there's a couple other tests I wanted to talk about. They're sort of optional tests in our program right now, mainly because we haven't really had we've kind of experimented with different methods over time of how to do these tests. So nitrogen and phosphorus are considered to be nutrients, and they're used by plants. Phosphorus is used they're both used by plants and animals. They can come from a number of different places. So they can come out of the natural environment. They can also come from being introduced from fertilizers or failing septic systems. And if you have too much of them, it can contribute to algae blooms or excess plant growth for instance, like in a lake. So in terms of the background on these, this is some information from EPA. So in terms of nitrogen, we're usually looking for them in the form of what's called nitrates. And there's a few different forms of nitrogen. So there's ammonia, nitrates, and nitrites. It can cause a problem to organisms if it's very high. Typically, that would be pretty unusual to find it that high. But depending on the contaminants, you could end up with a higher level of nitrates. Phosphates, again, are a nutrient. The most common form of phosphorus is called phosphate, which is that particular form, and it's involved in a lot of biological processes. There's no set standards, but there are guidelines for different ecoregions. So here's a chart that kind of gives you some of the ranges of what's considered to be good. So you want your level to be pretty low. So the closer to zero, the closer, as far as the water quality index, the closer to a 100 you'd be. So if you have a level of 0.3 milligrams per liter or parts per million, you can see that that would be essentially zero. So this is kind of the effective range that you would expect to see if you're monitoring phosphates. It would be somewhere between 0 and 0.3. And I'll just qualify this to say that I'm not an expert on these ones, and they are difficult to test for. But we and some local partners have been using a Lamont kit to do some testing, and we'll go through the details of how to do that at our practical training session. But essentially, this is the kit we've been using, and it's another titration type test. It's one that might be a little bit more difficult to do on site. So in some cases, you may want to take a sample back and do this sample off site, because it's unless you have like a table and you have some time and you have good weather on your monitoring site, it's something that just takes a little bit more time. And this is an optional test that we're sort of introducing, but I'm going to cover it in our practical training. The other test that we've implemented is conductivity monitoring. And these slides on conductivity monitoring are courtesy of a woman named Nicole Reiber, who was with our program. She was an intern with Whale Scout, and then she did some work with us. She did a capstone project with us, did some research into conductivity monitoring, and now she monitors water quality for King County. So conductivity is electrical conductivity, and it's essentially a measure of how well the water conducts electricity. If there's more dissolved ions in the water, it's going to have more conductivity. And typically that's associated with more pollutants in the water body. We have and testing, I guess you can test for conductivity as kind of a proxy for various contaminants without knowing the specific contaminant. So you can run some quick and easy conductivity tests without having to run, like I say, an expensive copper test or another test, unless you need to know that particular pollutant. So how you measure it is you basically have a little probe that just measures voltage flow between one electrode and the other. The units that we use are called microsiemens, which is written by that thing that looks almost like a little U and an S. That's the symbol for microsiemens. And we also typically, the meter will give us a corrected number as if the water temperature is at 25. So it does vary by temperature. So there's different things in the environment that can influence it. Electrical conductivity. So ions from the groundwater, runoff off of streets, runoff from landscapes, what kind of land use. So if there's a lot of roads, or if there's a golf course, say, versus like a forested natural environment, you might have different electrical conductivity. And water that's influenced by the tide, that could affect it as well. And there's quite a range for freshwater streams. So what you're going to find is if you start monitoring conductivity and really any of these variables, you're going to establish what we call a baseline, which is what's normal. What do you normally find? And so a particular stream in a non-storm condition, non-storm event condition, if you monitor it over time, you'll find that it typically holds fairly close to a certain point. And that's kind of your baseline. And that's going to depend on the stream. So for instance, if I measure Little Swamp Creek versus I go measure Swamp Creek versus North Creek, I may find that they have slightly different baseline numbers, but I wouldn't expect them to be super far apart. So once you have that baseline, the way that you can use that is, okay, now for some reason you discover that the number is far different than what the normal baseline is. That could be an indicator to you, just like if you see turbidity, it's an indicator that something's going on. If you measure higher conductivity, that could be an indicator that something's going on. And you can also find long-term patterns. So this is the device that she researched and that we're using. It's just a little inexpensive conductivity meter, and it comes calibrated. It also measures total suspended solids and temperature. And essentially you'll find that there's a relationship, and I don't know what the exact relationship it is, but there's essentially a relationship between conductivity and total suspended solids. So typically a device that measures one also measures the other. But then this one also measures temperature as well. And so we're providing these to our water monitors, as well as calibration solution. And you don't have to calibrate these every time you go out, but every once in a while we get the meters all together, compare them, and calibrate them. And from Nicole's research, it compared well against a more expensive conductivity probe used at UW-Bothell. So the procedure for using this conductivity meter is you can either collect it in a beaker. So this set of instructions describes using a sample collected in a beaker, but you can also just hold it in a flowing water body. So to describe the beaker technique, so you're going to rinse the beaker 2 to 3 times, fill it about halfway with sample water. You're going to turn on the meter, and you just don't want to submerge the whole meter. You just want to submerge the probe part. So it's about up to the lettering at that portion on the probe. You're going to gently swirl it as you read it, and the number is going to change. And at some certain point, the number is going to stabilize or change very, very slowly. So at that point, you're done. You're going to repeat the process 2 or 3 times, or 2 more times. You'll get 3 measurements, and you'll record the average. And then at the end, you'll rinse the probe with deionized water and dry it off and store it. So that's essentially our conductivity monitoring process. For calibrating it, it's similar to doing a conductivity test, but essentially you do, and these instructions are in the kits that we give you. Essentially you're doing like a conductivity test, but with this particular solution. And if you don't get the number that it says on the solution, then you go through a process to calibrate the meter so that it reads the correct value. Okay, some final considerations. I would say if you're new to this, I would recommend you start monitoring with an experienced partner. These tests that we went through, it seemed like a lot of detailed, complicated tests, but once you've done them a few times, they get a lot simpler. And I would just say, have fun with it. So at this point, I'm gonna stop our recording and stop sharing, and then I'll just take any final questions.